All right. Yeah, we'll go again this moment into another aspect of significance testing. I told you guys already that we have different tests we can conduct depending on the peculiarity of the situation. We already walked through the Z test. We also did the T test. Now we want to move into the chi-square test. It's a unique test and it's quite very easy to conduct. Just like the other two testing we did already, all you need to focus on is number one, you need to focus on what makes you to decide to use a chi-square test. So the why. Why do I use a chi-square test? Then the other thing you need to focus on is how do I conduct the test? Now, on the basis of the how, one of the main thing you need to focus on is the peculiarity of a chi-square test as compared to other testing. Number one, you need to know how to find the test statistics. I told you guys already that the test statistics is one of the most important part of any of this significant testing, because the test statistics, as I said already, is always obtained from sample data. And just in case you don't recollect, I told you guys that what really happens when we're dealing with significant testing is there is a default belief, there is a null hypothesis, there's a default hypothesis. A researcher believes differently that null hypothesis should not be. Now, you cannot go on now and because you had an issue with a default claim, a default hypothesis, then you go on to now establish your own hypothesis. No. In statistics, what you have to do is to conduct a test of which you will have to take a sample. So what always happens after a researcher wants to debate a particular default claim is that the researcher will go collect a sample. And that's why we say the test statistics is very important, because it is that test statistics that always summarizes, it's almost like the mathematical summary of your sample data. So you take probably a sample of 20 and you have the mean, the sample mean, you have the sample variance, you have the sample size, obviously. Now, if you are done with or getting all these different estimates, one of the things you want to do is to have a summary, a mathematical summary that from there you'll be able to use it to decide if you're going to reject or not reject the null hypothesis. That's what we call the test statistics. It's so important. It's what we use to always determine the final thing. And if you can observe from our test, from our t-test, the previous testing we have done, you will see that once we get something, we'll say we are going to check it if it falls within the rejection region. And if it did fall inside the rejection region, we would be rejecting the null hypothesis. So you see how important the test statistics is. Now, one of the things you need to look out for now is what is the test statistics for chi-square test. Now, also, one other difference between the chi-square test and every other one we have done is the use of a chi-square table. So if you notice when we were doing the Z test, we dealt with the standard normal distribution table, the Z table. When we went into the t-test, we had the t-table, which we have gone through that on how to check it. Now, you'll be dealing with a different table here, which is the chi-square table. And the chi-square table of course, comes with its own peculiarity of knowing how to check it. All right. So those are some of the things that I will just be bringing to your notice today. Now, the procedure of conducting this test remains the same. All right. It's the same way we have been doing it in terms of the methodology. The only difference is that, of course, a different test statistics, also a different way of checking the table, a different table, and also a different reason why you're going to be using it. All right. So let's get right into it. Now, a chi-square test is a very peculiar distribution, and it's categorized into two. So we have two different categories, all right, for which we can, two different methodology of, and the two different categories are all very important to note. And you have to understand when to use one and when to use the other one. Very simple. These things are too simple. You don't have to struggle with them at all. So chi-square, we have two categories. The first one is what we call the goodness of fit test. All right. And the second category is what we call test for independence. So we have the test for independence. Oh, I think there's a hen here. All right. So sorry for the breaking transmission. That was based on the network. So sorry about that. All right. So let me try and give you like a recap on some of the things I said before now. So we want to really get into chi-square. This is the first class. So you don't need to, as I always say to you guys, you don't need to get so hard on yourself. This is the first class, so just try and be calm. You're going to really understand it because it's quite very simple. All right. Now, look at the whole thing is just the same way you do the Z test and the T test. The only difference is, number one, the reason why you conduct a chi-square test will obviously differ, because the only reason why you're going to decide to use a chi-square is because of something. Not if it was, if it nobody would actually tell you to use a chi-square test in many cases. What they would mostly do is just give you a question. When you see the question and you see some certain features, then you know, okay, I'm going to be using a Z test here. I'm going to be using a T test here. I'm going to be using a chi-square test here. So we need to spend a little bit of time explaining on why do you use a chi-square. And that will all come through the explanation that comes on each of the different types of chi-square. So the why is very important for you to note, because if you don't know the why, then you won't be able to know what questions you're supposed to use a chi-square for. Now, the other one is the how. How do you go about it? I've sent you guys the table, so you can check your DMs for the table. Sorry, you can check the group page for the table. I expect you should have seen it by now. So the table obviously is very different from that of a t-square and also that of a z table. So you have to know how to check the table. Also, still on the how, there is something called the test statistics. I told you guys about this thing while we were doing the previous testing. The test statistics is one of the most important parts of every of your significant testing, because the test statistics is like the value you get from sample data. So take for instance, somebody said something, or let me say it this way, there is a default belief already. Now you want to oppose that belief. You want to bring in a different hypothesis, which we call the research hypothesis. Now, in this case, you cannot just go on and say because you don't believe what has been established, then you are going to change the whole narrative. No, what you have to do is to carry out sampling, pick out sample data of what you're trying to research on, get the mean, get the standard deviation, and get other important things. When you're done with that, you subject it to a test. Now, after you get the mean, yes, based on the last testing we did, that's the Z test and the T test. After you got the mean, the variance, the standard deviation, you then want to bring out a summary for all the values you've gotten. Now, that summary is what we call the test statistics. It's from your sample data. So your test statistics value, for instance, could be 3.22. This summarizes all you got from the sample data. It is this test statistics you then use, of course, based on the diagram you drew, whatever your critical value was, then you go on to check, does it fall inside the critical region? Does it not fall inside the critical region? If it fell into the critical region, you'll be rejecting the null hypothesis. If it doesn't fall within the critical region, of course, you do not accept the null hypothesis. You do not reject the null hypothesis. That's the whole basis of this testing. Now, you'll be having a test statistics also for chi-square. And by the way, I highlighted two different chi-square tests: the goodness of fit testing and the test for independence. They are unique in their own self. They all have there is a difference in how you test on both of them. We'll be talking about it very soon. Now, after getting your test statistics, of course, you then want to go on to deal with if you're going to reject or not reject the null hypothesis. Now, there's a table for this. You should have gotten it by now. One very important thing I want to say about test statistics, about chi-square, is that, if you recollect when we're dealing with our Z testing, we always made use of what we call a bell-shaped distribution. We always had our curve this way, and we call it a symmetric curve, symmetric about the mean. All right. I'm sure you guys should be able to recollect all this. So whenever you're dealing with your Z test or T test, you had the mean here. Of course, if you're using a standard normal distribution, your mean will be 0. Then if you are dealing with right tail test, you have this and so on and so forth. Now, there's a difference between chi-square and Z test or T test. Under chi-square, chi-square is not a symmetric distribution. Chi-square is a right-skewed distribution. One of the major things you need to note, chi-square is right-skewed. Is right-skewed, all right? Chi-square is not symmetric. Chi-square is right-skewed, all right? Chi-square is not symmetric. Chi-square is right-skewed. So that's probably what I want to even start with. Let me start with the graphical representation of a chi-square distribution. It's not symmetric. So again, I don't know if you heard what I said as regards the two types of tests before the network went out. But other chi-square will be looking at the goodness of fit test and the test for independence. They are all different, and I will explain to you. For test for independence, we also mention contingency table. You can say contingency table because we make use of what we call the contingency table, or a cross-tabulated table, or a cross-classification table. different ways we do call many of these things. We'll get there very soon. They are all very simple. Nothing, there's no big deal about this at all. Now, for the goodness of fit test, as I was trying to explain, when you hear goodness of fit, it comes with the word goodness of fit. How good does something fit something? In this case, for chi-square is how good does your observed value fit your expected value? This means you will have an expectation. So, for instance, let's say I expect this. Let's say I expect that in the 5 days of the week, we'll be solving a question very related to this very soon. Let's say I expected that in the 5 days of the week, in each of your classes, there are going to be 50 absent people every day. So Monday, 50 people are absent, Tuesday, 50, Wednesday, 50, Thursday, 50, and Friday, 50. Let's say this was my expectation, right? You can see, of course, I'm sure you guys already know that this is probably what will bring out your null hypothesis, because this is like, okay, this is what I believe. This is what I believe that, okay, 50 people are going to be absent every day. Monday, 50 people will be absent. Tuesday, 50 will be absent. Wednesday, 50 will be absent. Thursday, 50 will be absent. And Friday, 50 will be absent. Of course, it can differ from this. Now, let's say I had this expectation. Now, of course, somebody says, I'm not sure up to 50 people are going to be absent. I don't feel 50 people. No, I don't think you're saying the truth. I don't think that's actually exact. All right, let's go on and observe this. In this case now, we don't talk so much about sampling. We're talking about observing. So this was my expectation I wrote out there. So you go on to observe, all right, let's see what happens. On Monday, then they count the number of absentees. Let's say, for instance, we had 30 people that were absent rather than 50. Maybe on Tuesday, we had 41 rather than 50. Maybe on Wednesday, we have 35. On this one, we had, let's say, 38. And right here, we had 51, for instance. Now, the meaning of goodness of fit is just what you can see right here. You want to find out how good your observed value. This is obviously my observed value now. This was my expected value. How good did your observed value fit your expected value? It's just that simple. So all you need to do is to carry out a chi-square test. So once you have a scenario where you are having to do with observed value, oh, somebody did something, somebody was expecting this, and then this was what he later observed. Once you see a context like that in any question, know for certain that this is a goodness of fit testing you want to do there. Because I'm really trying to talk about why will you do a chi-square test. Don't worry, very soon I'll be coming to giving you the diagram of the right skewness of a chi-square very soon. But just to give you a little context on goodness of fit. So you see a question that says, this was expected, and then later this was observed. Now, you don't go on and just say, because this person, I don't believe 50 people are going to be absent in this place, and because of that, we're going to decide that what the person said is wrong. No, you have to go on to carry out a chi-square test, a goodness of fit test. So what you want to do is to observe. On Monday, observe. Now, this can also be related to probably a shop, maybe you have a shop and you're expecting this number of customers. You had expectation for every day of the week. This number of customers were going to come around. Now, you told people that, okay, on Monday, I'm going to be having this number of customers. On Tuesday, I'm going to be having this number of customers, and so on and so forth. Now, people say, oh, wow, I think you guys have more than this. I don't think it's okay. Let's see what happens. Let's observe. So you go on to observe the whole scenario and take your values down. So after observing, then you want to carry out a chi-square test, a goodness of fit test, to see if it did fit, if your observed value did fit your expected value. Does it make sense, guys? So a goodness of fit test is a statistical hypothesis test that determines how well your observed sample data matches an expected theoretical or population distribution. That's simple. How well your observed sample data matches an expected theoretical or population distribution. It evaluates whether discrepancies between what you actually observed and what you predicted is small enough to happen by chance. So we'll be going into how you're going to deal with this. Now, by the way, a goodness of fit test is actually very good for categorical data. Data that has to do with categories. You can see right here, this is the first category, Monday, a category, Tuesday, so it works very, you see, once you give me a question and I see that this has to do with categorical data, immediately my mind starts to draw towards chi-square test, because I know a chi-square test is very good for categorical data. So when you have categories, in this case now you have just 5 categories. You can see right now 5 categories is there. By the way, note that we're going to be talking about degree of freedom also under chi-square test, and in this case we're not going to be talking about it the way we said it under t-test. It's going to have to do with the number of categories. So note the word I'm saying when I said it's best for categorical data, and in a case like this value, this example I'm giving, this is 5 categories. Of course, this is observed, expected of a Monday, of a Tuesday, of a Wednesday, of a Thursday, of a Friday. Of course, it doesn't mean these are the only possible examples. You can have a 7 category question. You can have a question with 10 categories, but in this case, it's 5 categories. And that is very important to use to find your degree of freedom. You'll be using your number of categories to find your degree of freedom. So I need you to understand what categories actually mean, so that when we have to talk about finding degree of freedom, you will not have any problem at all. So that's like a very great introduction to this. Let me quickly have right now try to draw up the skewness of a chi-square test. Now, it's something I would love you to take note of, because of course, I told you guys already, you would not be drawing if you are solving a chi-square question and you draw a symmetric distribution. You are already telling the examiner that you don't know what you're doing. All right, because a chi-square distribution is not symmetric, it is right skewed. Now, if you have I'm just going to give you about 5 categories. 5 categories. So when you have 5 categories, of course, again, I will say, even though I'm going to be drawing this, the major thing, I will tell you what you need to just majorly do when you're dealing with a question under chi-square. All you need to do is not draw a symmetric distribution, but the way you handle your curve may not be as exact as the way I'm going to be drawing it right here. But just make sure you don't always have your curve being drawn as symmetric. Okay. So for this one now, first one I drew is when you have your category to be 1, just 1 category. This is the way it looks like. When your category is 2, this is how it looks like. Now, when your category is 3, it tends to have something like this. When your category is 4, it has something like this. When your category is 5, it tends to be like this. So again, I need to tell you guys that you may not be as exact as, even I myself am not as exact as it's supposed to be. But this is just a rough sketch I say, of the shape of your distribution. So it's not symmetric, it's right skewed. So most of the time, if you can note this, know it well, good. But majorly, you just need to always make sure you're drawing a rightly skewed distribution. All right. So now let's get right into it. Let's try and talk about some other important things. Now, I cannot overstate the importance of knowing how to set your null hypothesis and alternative hypothesis. I need you guys to know that you're not going to be given the hypothesis in literally chi-square is one of that tests where you will not even, in some cases, you will not even know, you will not even say anything that indicates this is chi-square if you're not able to read between the lines. It's one of the most simplest one, but also the word problems can be quite technical because it comes with the ability to do many of those technical, you put in technical terminology in it. So I want to talk about, I will try to stress on how to set your null hypothesis and your default and your alternative hypothesis for both kind of tests, both the goodness of fit and also the test for independence. So please make sure you are keen to what I will be saying, because don't expect that you'll be getting like somebody stating that for you. You need to know how to state it. By the way, we're going to have sometimes different words in our null hypothesis, sometimes, because it may not be very exact, like we say the same thing, but it must mean the same thing. It may not be the same thing, but it must mean the same thing. All right. So first of all, let me tell you guys what the test statistics is when it comes to chi-square. So by the way, the symbol for chi-square is tiled x with square. This is how a chi-square looks like. It's not like x, but it's like a tiled x with square. That's a chi-square. This is when you see something like this, you're talking about chi-square. When you see it in any question, the symbol like this, sometimes they don't want you to have to check the table. They don't want to fix in the table in your exam. So they will just write whatever the table value is. They'll just write that the table value was probably 1.712, something like that. There are times when they do this in exams. So they didn't want to really examine you checking the table. They wanted you to just use this. So note that when you see something like this, that's the chi-square. Now, what is the test statistics for chi-square? Very, very important. What's the test statistics for chi-square? So look right here. So calculated value, I'm going to put a C there because we'll be talking about the tabulated value, and we'll talk about also the calculated value. So for the chi-square calculated, it's something you must note. It is the summation of the observed value so the test statistics for chi-square is what you see right here. You of course, I believe you've been able to know that of the z-test, and that also of the t-test. This is for the chi-square. All right. So note this very much. It's the summation. So what you do right here, remember the table I showed you. You have the observed, you have the expected. So you want to go on to have the observed minus the expected. You square that value, divide by the expected. So you do for each of the categories, then you add every one of them up. That's the way you deal with the test statistics. Quite very simple. You know, I told you guys this thing is very simple. The only difference is you knowing what and what to do. So if you had like I gave you earlier 50, 50, 50, 50, and 50, let's say 31, 41, 38, 50, let's say 35. Let's say, for instance, we have this, all right? What you want to, if this is the, of course, this is the expected, and the one right on top is the observed. So what you want to do in a case like this is the observed, this is the expected. So what you want to do is to go on to say 31 minus 50 over 50, of course, this square, plus you want to have 41 minus 50 plus 38 minus 50 square over 50 plus every other one. So you want to sum this all up, whatever you get, and that will be what will represent your test statistics. That's just all. And just the same way, you have our data set like this. Of course, what you want, okay, let me just draw it. We also deal with rejection region and acceptance region. So let's say my critical value, of course, you know, this is always the one that I represented on the extreme tails. Now, this is the rejection region. If 9.5 was the critical value, that represents the position of where your test statistics could be for you to be rejected or where it could not be, and it would not be rejected. So if your test statistics, for instance, let's say we got our test statistics as 5.5. Let's say our test statistics when we're done with all this using the test statistics right here. Let's say we got 5.5. Obviously, you want to look through on this and say, where does 5.5 falls under? This is 9.5. If the critical value was 9.5, 5.5 obviously will fall before 9.5. And obviously, that doesn't represent the rejection region. So in this case, we do not reject the null hypothesis. Now, if, for instance, let's say we got 15.5 as our test statistics. Of course, 15.5 falls, in this case, it falls inside the rejection region. So we say we do not, we reject the null hypothesis. So it's that simple. It's the same procedure for how we have been testing. The difference is just for you to understand, number one, why do you use a chi-square? Number two, how do you make use of a chi-square, which involves you understanding the test statistics, knowing how to apply the test statistics, knowing how to check your table. Of course, checking your table will come with some other things which I'll be talking about very soon, the degree of freedom and how you use the degree of freedom, and also, of course, following the same procedure on how you used to test before. If it falls in the rejection region, you reject. If it doesn't fall, you do not reject. So that's just as simple as ABC, right? Now, guys, let's quickly talk about how to check the table. All right, the table of the chi-square. How do you check the table? I believe you guys have seen and observed the table you have right there. It's very easy to check. It comes with no complexities at all. Know what your degree of freedom is. All right, the degree of freedom thing you must know for you to be able to make use of your chi-square table. Now, the other thing you must know is your significance level. All right, so your significance level plays a very key role in being able to get the value on your table. Now, you would see two things. The first one, the degree of freedom. So you have the DF. Then you also have the significance level. All right. So what you have on this other side of things is your chi-square with its corresponding significance level. Note that significance level. You can see it indicated there. So everything you're seeing, you'll be seeing, I believe you can see it if you have the table right with you. You would see the first one was the chi-square for a significance level of 0.995. Because that significance level is quite very high. You keep moving, and then you will see that of a chi-square for when you had 1.00, and then you had the next one being the chi-square for 0.05. All right. Then you see that of 0.025. You see that of 0.01. You see that of 0.005. So those are the ones you have in the table you have right with you. Now, just as simple as ABC. All you have to do is, number one, note what your freedom is. And then if you're dealing with alpha, for instance, if your alpha was 0.05, then you go under the degree of freedom. Let's say your degree of freedom now was 9. You go and check for 9 under the 0.05. Whatever value lies there gives you the value for your critical value. It gives you a critical value. Now, let me then address, how do you find your degree of freedom? Your degree of freedom comes with a very high level of simplicity. All you need to know is the number of categories of your data. So in a case like this, where I dealt with, in that case, you may have 10, depending on whatever question you are asked. For this question right now, I have 5. Degree of freedom for chi-square is given as k minus 1. K here represents the number of categories you have. So if this is I need to state this, that we're dealing with goodness of fit test, because the degree of freedom for test for independence is different. For goodness of fit test, your degree of freedom is the number of category minus 1. So in the case where the number of category in this case now was 5, my degree of freedom will be 5 minus 1. That would be 4. So I wanted to check the table value, the critical value of this. I will go under degree of freedom 4. And I will, depending on whatever level of significance I'm dealing with, if I'm dealing with 0.05, I will come under 0.05 and pick out my values from there. That's how I'm going to get the degree of freedom. Sorry, that's how I'm going to get value. And I'm going to place that value on a right skewed distribution. Let's say my value was 7.8 or something. I'm going to place it there. I'm going to now go on to find my test statistics. And whatever my test statistics gave me, I'm going to go and check it. If the test statistics is going to fall within the rejection region, I'm going to be rejecting the null hypothesis. If it's going to fall in the acceptance region, then I'm not going to reject the null hypothesis. It's that simple. All right. Now, probably the last thing I need to state very clearly is, how do you set your null hypothesis? And then from here, we'll be solving a few questions, and then we are out of here. How do you state your null hypothesis? In this case, this is quite different from that of z-test, where you have to maybe you will be saying the average population mean being equal to this, and then also this will say greater than or equal to, the way we did it on that z-test. This is different, all right? And in some cases, you will have to be making use of words to state your null hypothesis. Now, let me just give you the brief of how to state your null hypothesis. Dealing with goodness of fit, please, I need to be very emphatic on the fact that I'm focusing more on goodness of fit in this discourse I'm having right here. It is goodness of fit I'm dealing with. Because when we come to test for independence, it's going to be a different thing entirely. So for goodness of fit test, if you want to state your null hypothesis, please make sure that, because as I told you already, it's not every time you may be able to put things like mu equals to 100 or something like that. In some cases you are able to, in some cases you may not be able to. But there is something that you must always have in your null hypothesis. Your null hypothesis must state that the observed actually fit the expected. Your null hypothesis must state, I repeat, that what you observed was fitting, there was little or no discrepancies. So it was fitting with your expected. So in a case like this now, let's say I wanted to state a null hypothesis for this question, where I had to do, don't forget what I was trying to do with here. I said, let's say people said, or the default belief was that in your class, for instance, 50 students are going to be absent every day. So on Monday, they expected 50 people. They expected 50 people to be absent. On Tuesday, they expected 50. On Wednesday, 50. On Friday, they expected 50. Now, they went on to observe for a week. Of course, don't forget that's like the sampling, because this was the expectation for every day of the week. They then picked a week to observe whatever was happening right in that class. They discovered that 31 was absent on Monday, 41 on Tuesday, and so on and so forth. Now, what you want to say in your null hypothesis, you want to say that, okay, what I observed was actually fitting with what I expected. So the default claim is what I actually saw. That's how you're going to have to state your null hypothesis. Your alternative will obviously say it wasn't it. All right. So if you are rejecting the null hypothesis, obviously that means, because don't forget, the reason why you carry out sampling, you observed it, is because somebody felt, I'm not sure that's the case. All right. I'm not sure that's the case. Somebody was feeling it's not 50 people. It's not 50 people. So your alternative, your research hypothesis will say it's not the case. When I finish observing, it wasn't fitting with the expected. So these two hypotheses must carry this context. All right. So look at this case now. When I have this scenario, I probably want to write equal frequencies as my null hypothesis. I told you guys already that sometimes the wordings of what you may write may be different, but in the end, they must still have the same context. So when I say equal frequency, that's what I mean by this is that, the observed actually had like an equal frequency with the expected. So what we observed was it did fit what we expected, equal frequencies. All right. The alternative will obviously be unequal frequencies. That means it wasn't the case. It did not fit. Unequal frequency, that's just the way you have to translate your null and alternative hypothesis. For the last time now in this class, I want to really state this. Make sure that your null hypothesis has the context of what we observed did fit what we expected. And then your alternative hypothesis should say otherwise. All right. Now, let's try and solve one question, and then we'll see if we can still solve another one after. Maybe one or two questions. I think that would be nice. And then we would close up. So guys, pay attention to this question. It's going to mirror exactly what I just did. This scenario, this one we did about absentees. All right, just a different a school principal would like to know which day of the week students are most likely to be absent. So this school principal wants to know which day of the week students are most likely to be absent. The principal expects that students will be absent equally. Now, look at now. I told you guys already, nobody will mention chi-square. So you need to be very careful. Don't expect to hear things around, this is a chi-square distribution. Using chi-square solve this. No. Most of the time, you will just see a word problem. And from there, you'll be able to know if you're going to be using a chi-square or not. Now, the school principal would like to know which day of the week students are most likely to be absent. The principal expects, of course, whatever is being said next is going to camp your expected value. The principal expects that students will be absent equally during the 5-day school week. So the principal is expecting now that during the 5 days of a week, going to be equal absent on Monday, will be absent. All right. He expects that there's going to be when it comes to absentees for that 5 days school week. So the principal selects a random sample of 100 students. They had the highest number. The observed and expected result are shown in the table below. Based on this result, do the days for the highest number of absentees occur with equal frequencies? Based on this result, do the days for the highest number of absentees occur with equal frequency? If you observe this question now, there's nothing in here that even mentions chi-square at all. That's why I try stressing on you understanding why you should use a chi-square. Everything being said here is just a word problem. Nothing about anything that indicates chi-square if you don't know what chi-square is all about. The last thing they wrote there was use a 5% significance level. That's all they said. So you know this is a testing, but they won't tell you which test you're actually going to be doing. Well, how do we know? Look at the table they gave us. This is how the table was. We're told that, of course, we have observed absences. When I start seeing something like that, I already know this is a goodness of fit test because this is a kind is actually best for categorical data. Now we're presented with the days of the week. We had Monday, we had Tuesday, we had Thursday and Friday. Now we're given 20. Of course, he expected equal. This is what he expected. Don't forget we had 100 students. So we had 100 students, and it's expected that they're going to be absent equally. They're going to be equal number of absentees for the whole 5 days. So that means we'll be having 20 for each day. All right. So was expected. Out of those 100 students, the number of absentees for every week is going to be equal based on the context of the question. Now, but what was observed eventually was that on Monday, 23 were absent. On Tuesday, 16 were absent. Wednesday, we had 14. Thursday, we had 19. Friday, we had 28. All right. So the question is for us, the question said based on this result, do the days for the highest number of absences occur with equal frequency? So do we have equal frequency? That means, is it what this guy was expecting? Is that what happened after the observation was done? So of course, as I said already, this mirrors my null hypothesis and my alternative hypothesis. I don't need to restate this. This was when I was explaining the previous one. But this is how I'm going to state mine, which is the fundamental thing you must always do. When you have a question, always try and state the null hypothesis first. And it must be very great because the basis of your test is based on a claim. If you cannot state the null hypothesis well, let me take for instance, let me say you wrote unequal frequency as HO now, for instance. When you're done with your testing, I hope you know you are going to be saying, oh, I rejected the null hypothesis. So if unequal frequency was what you were rejecting, when you're supposed to reject equal frequency, I hope you know you have done wrong testing in that case. So the stating of your hypothesis is quite very key to the success of whatever testing you are doing. So you need to be able to state what the default hypothesis in the question was saying, and you need to be able to state what the research hypothesis was also saying. So that at the end of the day, when you are done with making a decision, if you are deciding to reject the null hypothesis, you'll be rejecting what you're supposed to reject. So you understand the importance. So at the end of the day, if you said I rejected a null hypothesis that was not actually supposed to be the null hypothesis, you would have failed that question already, because you're supposed to conclude that maybe the data set actually fit each other. Or sorry, you're supposed to conclude that data set doesn't fit. Probably you're supposed to say, what they was expected was not what actually happened, did not fit the expected. Now, because you had stated the wrong hypothesis, to reject that they actually did not fit, you are rejecting unequal frequencies. So if you are rejecting unequal frequency, that means you'll be stating that there is equal frequencies. So you see that you have gotten it wrong in that case. That's why you have to always state your null hypothesis. There's nothing as important as stating your null hypothesis the right way in any of the testing. It's very, very important. So always know how to state it. And I told you again, just for the sake of saying it just one more time, probably I still say it again because I love calling for emphasis on things like this. Your null hypothesis should say that what you observed did fit your expected. Anyhow, you're going to say that in any context. And then your alternative hypothesis should say, no, it did not fit. So in this case now, this was the expected, that equal frequency were going to happen. If these things did fit, if the observed fit this, then that means we're supposed to have equal frequencies. We're supposed to have equality there. But it did not fit. If it did not fit, that means we're going to be equal frequencies. So your null hypothesis say, oh, there's a fitting here. Your research hypothesis say, oh, there was no fitting. That's the whole context. All right. Now let's solve the question. Now we're done with stating the hypothesis. So can we now go on to draw the diagram? This is k being 4, sorry, k being 5. So I told you guys that you may not be as exact as this, but you're going to draw this. It's going to look something like this. All right. This is how I told you it's not a symmetric distribution, it's a right skewed distribution. Please take good note of that. It's a right skewed distribution. All right. Now, for us to know where the rejection lies, rejection region lies, the critical region lies. Again, note all these terminologies. Rejection region, critical region, they're the same thing. We have to go get the critical value. We are going to be able to get our critical value from the table, the chi-square table. And as I told you guys already, for you to get the values from your chi-square, you need just two things. Number one, you need your degree of freedom, and you need your alpha value, your level of significance. Now, for this question, you are told to take your alpha value to be 0.05. And you are told to take, of course, you are told to take your alpha value. And you can observe that, how many categories do we have here, guys? Can I get some response in the chat box? How many categories do we have based on what we have right here? How many categories do we have? How many categories do we have? Okay, thank you very much. 5. We have 5 categories. Of course, for people wondering, how do we know the number of categories? Right here, we have 1, 2, 3, 4, and 5. So we had 5 categories. So our K is 5. But degree of freedom is not K. Degree of freedom is gotten as K minus 1. So we have, in this case now, we have 5 minus 1, which gives us the value 4. So our degree of freedom is 4. Our alpha is 0.05. So we have to go on now. On our table, we want to look for 4 right here. We want to look for the value 4 on that degree of freedom. I want to go on to find the chi-square with 0.05. So if you can do that quickly, can you run into your table and go find what is the answer what's the value, the chi-square value that has degree of freedom of 4, the significance level of 0.05. Can anybody check the chi-square value quickly and give me your answer? Somebody said 14 points. Somebody said 14.860. Is that correct? Can anybody check for something else? Okay, the person has retracted his answer. Somebody said 9.4. Okay, the same person said 9.488. Probably observing that was not perfect. And somebody is giving a conclusion. You're supposed to follow through on what we're doing. What was your critical value? Guys, what's the critical value? You have a degree of freedom of 4 and then a level of significance of 0.05. 0.05. So if you check it right there, I can see a value of 9.488. Oh, why are you guys getting 14 points? What are you guys doing that is giving you 14 point something? What are you checking? We're talking about What are you guys checking that gives you 14.8? You guys are checking, I think you guys are checking 0.005. Many of you are checking 0. Can you see? That's a very big mistake. You're checking 0.005. 0.005 is different from 0.005. 0.05. Alpha is 0.05. This is not the alpha. This is the alpha here. So if you check 0.05 now, what did you get, guys? Yeah, it was 0.005 that gave you 14.860. So what did you get for 0.05? Thank you. 9.488. Actually, not 448, but 488. Somebody is getting 7.815. 7.815. That person is checking 3. Atom is checking for 3 under 0.05 instead of checking 4. That's what gave you 7.815. You're supposed to check 4 under 0.05. So, guys, maybe you get perfect in that. It's actually 9.488. So 9.488 is your critical value. Right? So you have something like this. Of course, this will represent the critical region. All right? That will represent the critical region. We have gotten our diagram right. Of course, we've been able to highlight the critical region lies and where the acceptance region lies. The next thing now, so we know already now that once we enter inside this spot, is that if our test statistics value fall within this place, we are going to definitely reject that null hypothesis, which is equal frequencies. And if it falls within this place, we are going to not reject the null hypothesis. So we need to go find our test statistics now. All right. So we need to go find our test statistics. That's the next important thing to do. Now, our test statistics, obviously, as I told you guys already, our calculated value is giving us the summation observed minus expected square over expected. So you guys want to do, what you guys want to do right now is, oh, I see that this is not in scope. Observed minus expected square over expected. All right. So what you want to do right now, which is the what a very, very important thing also, is you want to go on now to say, this is the observed, 23. This is the expected. So for each of them, all right, permit me to get out this I want to go back to, I want to clean up this. So what you want to do now is to say, for the x calculated, the chi-square calculated value, you'll be having observed is 23. You have 23 minus 20 square. You square that first category. All right. So you want to add up that for Tuesday. The observed is 16. That will be 16 minus the expected is 20. You square that over 20. You want to do for Wednesday. Wednesday is 14 minus 20. You square that over 20. You want to do for Thursday. You have 19 minus 20 square over 20. Then you want to do for the last category. That's Friday. So can you guys fix this up in a calculator very quickly and tell me what you got? This is the test statistics. What did you get for this value as your test statistics? Fix all this in a calculator. Of course, 23 minus 3, that's 3. 3 square, that's 9. 20. The next one we have 16 minus 20, that's minus 4 square, that's 16 over 20. The next one we have 14 minus 20, that's minus 6 square, that'll be 36 over 20. And the next one we have 19 minus 20 square over 20. 19 minus 20 is minus 1 square. And then we have 28 minus 20 square over 20. So add all this together. I can see the values being written there. The values, the total answer you're getting is 6.3. All right. Now you've gotten your test statistics, and I told you how important this value is because this is the value you're going to be using to decide if you're going to be rejecting or not. Now we've gotten as our test statistics. We want to then go on to observe, where does this lie? Does it lie inside the rejection region or outside the rejection region? From your observation, does it lie within the rejection region or outside the rejection region? What's your conclusion on that? Is it within the rejection region or not within the rejection region? Outside the rejection region. So obviously, if this is 9.4, 6.3 obviously will be before 9.4, probably somewhere here. So it's inside the rejection region. So we do not reject the null hypothesis. So our conclusion now, of course, I told you guys already, very important also to make the right conclusion. So for this question, we do not reject the null hypothesis. But I told you guys already, please don't just, as much as sometimes you may see that being written somewhere, it's always good statistically to always state you did your test or the confidence level, depending on which one you want to use. So we can say and always try to, I mentioned 3 important points when trying to make your final decision. Number 1, state the confidence level or the level of significance you did your test. Also, what, all right, were you rejecting or were you not rejecting? Then the last one, as much as you can, try to frame your answer. It may not be at even the first sentence, it may be later. Try to frame your answer in the context of what the question said. Maybe you would say, for instance, like we said, at a 5% significance level, we do not reject the null hypothesis. And therefore, we conclude that we have equal frequencies. All right? So, or you can say it based on the way the question said it. We conclude that the days for the highest frequency of absentees occurs with equal frequencies. So try and always frame your answer, your final conclusion on the basis of what on the question was saying. All right. So let's try and solve a question and see. You guys should be much more stronger. Now, this next question I want to solve is going to bring you guys to a different context. All right. It's going to bring you to a different context. So in this case now, you can see that we just had it being, we had more like a very straight up data set, 20, 23. We had 23, we had 20. In some other cases, which is what the next example is going to say. The next example we want to solve, you'll be using percentages. So you will have to bring out your values yourself. Let's get right into it. You'll see what I'm saying. All right. Now, I'm going to write, let me just, guys, can you give me your feedback? How well the chi-square at this point? Give me your feedback quickly. Let me hear from you guys. Are you guys coping well? Is it going well? Now, okay. All right. It's going well. Good. Now I'm going to give you this question in which you would have to similar to that. The only difference is that in this case you would have to bring out now the table I want to show to you represents the distribution of the number of customers you get each day. So this is a different context now where you're dealing with customers. Probably you have a shop or something. So, and of course, it still has to do with days of the week. So we have the day of the week. So we're going to be using, let me just write expected. Okay, let me increase this because, so this is expected. Now, this is the difference now. Your value of expected was given in percentage. All right. Now you're going to understand why I'm giving this question in a moment. And you are given the observed data. So this is what's happening here. For this particular shop owner, on Monday, this shop owner expects 10% of a customer. Monday, 10% was expected. On Tuesday, this person expected 10% also. On Wednesday, she expected 15%, probably for some certain reasons. On Thursday, she expected 20%. Your values are given in percentage. On Friday, she expected 30%. And on Saturday, she expected 15%. So look at what's going on right here. If you sum the total percentages here, you see it's all 100. It's going to be 100. This 50, this 30, this 20. That's 100%. Meaning that this person actually for the whole week, this is the way she expected her customers to be divided, spread across each of the days of the week. She expected that for the whole 100 customers, for the whole 100% of customers she's going to have in a week, she expected that 10% of them will come on Monday. So let's say, for instance, she had 500 customers in a week. She expected that this is how it used to happen. On Monday, 10% will come. On Tuesday, 10%, another 10% will. On Wednesday, 15%. On Thursday, 20%. On Friday, 10%. On Saturday, 50%. This was our expectation. That if she had 500 customers in that week, this is how they are going to be distributed across the day. Now, I did not say it's, of course, I'm just saying, for example, it was 500 customers. Based on the data you're going to see here, you're going to know how many customers she had in the week when they observed it. Now, look at the observed value now. When they went on to observe what was going on, they noticed that on Monday, now, not in percentage now, this one is in actual value. 30 people came around. On Tuesday, 14 people came around. On Wednesday, 34 people came around. On Thursday, 45 people came around. On Friday, 57 came around. And on Saturday, 20 people came around. This was what was observed, of course. Now, I told you guys already, when you don't even see so much of this being written in the context of chi-square. Once you see categorical data, especially when you are seeing observed and expected, just know that you're dealing with goodness of fit test. You're told to test this as 0.05. And the question was, how good does this distribution actually fit the observed data? You know, I told you guys already, goodness of fit has to do with, okay, I had an expectation. How good does the distribution this person had, look at the way she distributed the whole thing. Fit the observed value. Did it go the way she expected? Were they fitting? That's the whole thing around goodness of fit test. So how good does this distribution actually fit the observed data? That's like the question we want to solve, want to answer, and say, you cannot go on now and say, I want to say this is expected value 10. That would be very wrong because they already indicated to you that expected value was written in percentage, not in actual value. Observed was actually written in actual value. expected was written in percentage. So you have to be mindful of that. Don't go on and use 10 as your value here and say, I want to solve the test statistics observed minus expected, and you're saying 30 minus 10 over 10. You'll be very wrong because this is in percentage. So what you need to do is to go and solve your expected value to actual data, no longer percentage, because you cannot want to use percentage and not percentage. It will not give you the right answer. All right. So you need to go and find out what was 10%. Yeah, what's the actual value for 10%? What's the actual value for 15%? What's the actual value for 20%? Now, how do you know that this woman expected that in the week she's going to be having 10% distributed on Monday? So the question you need to ask yourself is that in that week, how many people came around? Go and sum this whole thing now based on the observed. Sum all these things together. 30 plus 14. Can somebody do that quickly? 30 plus 14 plus 34 plus 45 plus 57 plus 20. Do the solution, the addition of all those values. What did you guys get? The total was what? What's the total of that? 200. Somebody's asking if the two are in percentages. Two are in percentages. Actually, that's not going to actually be possible, just so you know, because you need something that will actually give you a pointer of where you are going to. The fact that you observed 200 people for the week is what you're going to be using to now bring out the percentages for the expected. So if both are in percentages, it's not going to work out that way. Except if they now give you something else and they said use this value as the total. No, it's not actually going to be very intact that way. So from what we see here, we have 200 people that were observed in that week. Now, based on this woman's expected that in that 200 people, 10% were supposed to be distributed Monday. Guys, what was our expectation for Monday then? Now, let me say expected, not percentage now. Let me just write it that way so that you guys can relate much better. Not percentage now. The actual value is what I'm actually probably supposed to say here. Actual value now. Now, based on what this woman said, she expected 10% on Monday. So, guys, what was our expectation in actuality here? What was the actual value she was expecting here based on 10%? Who can tell me that? If she had 200 people in the week, what did she expect was supposed to happen? 20. Thank you very much. 20. So she expected that 20 people were supposed to be. If she had 200 people, she expected that 10% was going to be on Monday. Now, the truth is, if your observed value was 500, that means she would have expected 50 was supposed to be distributed on Monday. If the observed value was 1,000, she would have expected that 100 people, that's 10% of 1,000, 100 people were supposed to be on Monday. So it's very flexible. It's not something you have to be rigid on. Whatever observed value, the total number of it to be distributed on Monday. So what's going to be, of course, these 2 days is going to be 20. What's 15% of 200, guys? What's 15% of 200? Oh yeah, shoot the answer quickly. That's 30, right? Okay. And what's 20% of 200? Of course, that will be 40. What's 30% of 200? What's 30% of 200? That will be 60. Let me take this out of here. What is 15% of 200? Okay, we did that already. That'll be 30. Okay. All right. Now, look at what we have right here. We've been able to diffuse the whole percentage stuff that was probably supposed to be like a trap for students. We've been able to bring it out now to the actual value, which makes it very much solvable at this point. Good. Now, we are done with that. So the next thing we can now do is to start solving now the right way. So guys, I want you guys to start solving this based on the last example we solved. Of course, I'm going to solve it myself, but those of you that know what you're doing, start solving right immediately. Okay, so I want to start solving first from stating the hypothesis, which is quite very important. The hypothesis, very important. So we have, can somebody tell me what the null hypothesis would be? Can you just give me like a very quick take on what you feel the null hypothesis will be? Again, as I told you already, we may not have the same word being said, but it must mean the same thing. So I told you what should be when you're dealing with null hypothesis. What should be the context? The context must always be that there was a fit between the observed and expected data. There was a fit. So what do you feel you can write here? Can you just tell me? Tell me, what can you tell me? Can you just write something? You're using my note. That person that said Donald Vision is correct, you're using my note. Give me your own. Give me your own context. You're using my note. You can say more of, okay, the Donald Vision is correct is good. I like that. Or give me your own context. You can say things that has to do with, just make sure it mirrors that there was fitting. All right. I want to get, but imagine you, of course, imagine you don't have my notes. What were you going to say? Can we do that in just like 2 minutes? Can you, I want different people to give me their own way of saying it. Say that the observed values and there was fitting between the observed and the expected value. You can say things much, you know, you may not have my notes right in front of you. Now, I used the owner distribution is correct, all right, as my null hypothesis that the owner distribution is actually correct. The meaning of this is that what this lady expected actually was the case. That means she was expecting 10% on Monday. Oh, wow, she got that. So when we went through the test, if we're going to be accepting the null hypothesis, that means we're accepting that what the woman expected was actually the case. That means our observed and our expected, there was fitting. They did fit. So this was our expectation before, 10%, 15%. When we're done observing, oh, we actually noticed that there was a fit between what she was expecting and what we later observed. That's what your null hypothesis should always say. So we're saying the null division is correct. That means what she actually observed, sorry, what she expected was actually good. It was correct. Now, of course, I can go on to say owner distribution is not correct. In simple terms, is not correct. Simple. That means there was no fitting. We noticed that there was great discrepancies between the observed and the expected. All right. So that's like a good way of stating your null hypothesis. The next thing we want to do now is to go on to plot our distribution curve. Don't forget, it's a right-skew curve. It's not a symmetric curve. We're dealing with how many categories in this case? We're dealing with 6 categories. So again, it's going to look more like something like this. And the next thing to do, this is just a boring right-skewed curve. The major thing we need to do on this right-skew curve is to make this have a rejection region, which we can only do by going on to find our table value, our chi-square table value. So we need to go on now to find our chi-square table value. And of course, for you to find our chi-square table value, you need the degree of freedom and you need the significance level of significance. So your significance level was given as 0.05. The degree of freedom is gotten, you get that one yourself, and it's gotten as k minus 1. K representing the number of categories. And how many categories do we have right here, guys? How many categories do we have? How many do we have? Okay, 6. I can see somebody saying that. 6. We have 6 categories. Of course, you can see them right here. Please don't count this as a category. Oh, you guys need to be smarter than that. This is 1, 2, 3, 4, 5, 6. So we're dealing with 6 categories. So we're going to be having 6 minus 1, which is what? 5. So now what you want to do is to go on your table, go under degree of freedom. You want to check for 5, and you want to cross that with the chi-square for 0.05. Whatever value you get under that is what you're going to be picking. So if you observe, can you guys tell me what you saw when you decided to make the crossing of that? Okay, 11.07. Are we all on that page? Do we all believe it is 11.07? 11.07. Yeah, actually that was correct. 11.07 is actually very correct. So 11.07 is your critical value. All right, 11.070. So this right here represents your rejection region. So anything that falls inside that spot, we are going to certainly be rejecting. So the next thing to do now is to go on to find your what? Your test statistics. Your test statistics, sorry, this is going to be up. Your calculated test statistics, as I told you guys already, it is observed minus expected all square over expected. So what you want to do now, and I want you guys to do this in some few minutes. Probably let me give you like 1 minute. Let me give you guys 1 minute to find these test statistics. Now you cannot use this percentage value. I told you guys that already. So you want to use the actual value. So what you want to do now is to say observed 30 minus expected 20 all square over expected as 20. Of course, you'll be adding that with every other one that you can see there. You can see this one will be 14 observed minus expected square over 20 expected. This one 34 minus. So you have to do that for the whole 6 categories. So what's your value? What did you get as a value for your test statistics? Somebody said 6 point what? 6.971. Is that correct? I don't think so. I don't think the answer is 6.971. Somebody said 11.4. Okay, that leans more to the answer. Anybody getting the answer as 11.4? What's your test statistics value? So what did you get, guys? Test statistics value was gotten as what? 11.4. Actually, that was actually correct. So 11.44 is the value for the test statistics. So guys, getting 11.44 as a value, what do you think? Am I going to be rejecting or not rejecting the null hypothesis based on the critical region I have in front of me? So what's your decision? 11.4 statistics. Am I going to be rejecting or not rejecting the null hypothesis? Somebody said, is that Jimmy? Why don't you understand? What's like 0 observed minus expected, all square over expected. This is the observed, 30. This is the expected, 20. You fix this up in calculation. 30 minus 20, square it over 20. This is summation. You are adding the next entry. 14 minus 20, observed minus 20, all square over 20. 34 minus 30, all square over expected, which is 30. Do that for every of this category, and you are good to go. When you fix this in a calculator, or depending on how you decide to calculate this, you'll be getting a value of 11.44. You can confirm that quickly. All right. The rejection part is very simple. This is the table value. If you want to get your table, number one, you have to know what the degree of freedom is. Is always category, the number of category minus 1. In this case, now we have how many categories here? 1, 2, 3, 4, 5, 6. That's 6 categories. So our degree of freedom will be 6 minus 1, which is 5. So our degree of freedom is 5. If you open the table, you will see there's a spot for degree of freedom. It has different numbers under it. There's a place where you will see 5 there. Now, if you look at the columns for the first row, you will see the chi-square written with different level of significance. You will see the first one being, I think, 0.995, and so on and so forth. Then you will see, because we have our level of significance here at 0.05, so you'll be going under the one of 0.05. So you will trace 5 under that of 0.05, and you pick out your value from there. When you pick out your value from there, you will observe that if you're doing chi-square of 0.05, you'll be getting 11.070. Now, that will be the mark, the critical value, the place where we're going to be deciding where we're rejecting and where we're not rejecting. So if this is 11.07, everything to the right, anything there is going to represent our critical region, and everything to the left represents our acceptance region. Very simple. You go on to find the calculated value, the test statistics. You got it as 11.44. You go back to check this. Does it 11.44? If I'm using a number line, does 11.44 false come before 11.070 or come after it? That's the question you have to ask. Looking at 11.44, it comes after 11.07, meaning that it's going to obviously fall within the rejection region in this case, because 11.44 is greater than 11.07, meaning it's going to be falling inside within the rejection region. If it was less than 11.070, it would have fallen in the acceptance region. So therefore, in this particular scenario, we are going to be reject it, and state the level of significance or confidence level you use. So I'm going to be saying at a level of significance of 0.05, I reject the null hypothesis. All right, and conclude that the Hohner distribution is not correct. All right. So Jimmy, can you give me my feedback if what I said was quite clear to you? All right. So this is where we're going to be stopping for today. It's great that you guys already have the basics of this. Ademola, I saw what you did. Thank you very much. That's no matter how little it is, that's of course it's not going to go unignored because it came from probably an appreciative heart. So that's great, and do well to enjoy yourself, and I wish you all the best in your coming exam. And for every one of you that's been here part, make sure you as much as you can get more questions. This is all about goodness of fit. The basics are just the things in questions cover next, similar. So we'll be doing that when we have the opportunity next. So guys, make sure you do take care of yourself. Make sure you study well. I wish you guys the very best. All right. Good night, everyone. Good night, everyone. Do enjoy the night. Good night, everyone. Take care of yourself.